In today's video, we're going to talk about polar coordinates and polar graphs. We're basically going to learn a new coordinate system, a new way to graph points that kind of correspond to this specific type pattern we have here. And what's going to happen is we're basically going to think about this as we would in trigonometry, right? As we have some angle theta and some distance kind of away from the origin, is how all of the points on our polar system are created. So let me draw a point here, and that's going to be the point r comma theta. Okay, r gives the radial distance from the origin, and theta will give the angle from what we call the polar axis. So I'll have some radial distance from the origin and some polar axis there. There's my origin, and my polar axis is what we think about as really the positive x-axis. R is described as the distance from 0, 0, distance from the origin, r. And that green arrow there represents my theta. Theta is the angle from the origin, from the polar axis. I misspoke. So think about this as, theta goes counterclockwise away from the polar axis, just as it would in the angles that we know on our unit circle, right? And r is the distance from 0, 0 from the origin, okay? What I have here is what we call a polar graph. This is a polar graph. This is what it looks like. You can buy graph paper like this. Basically, the idea is we have a bunch of these intersecting lines that all intersect at the origin. We think about kind of things moving out radially in a circular pattern, all those concentric circles there from the origin, okay? So different r values will kind of move outward, out kind of away from the origin. And then each of those lines kind of intersecting at the origin will help us determine what angle we're at, what is our theta. So I want to graph some points here first. Let's do r theta we'll do 2 comma pi over 3. Okay? So basically the way I think about this is I have to go out 2 units from the origin in some specific direction, basically the pi over 3 direction. So we have to remember pi over 3 is 60 degrees. So each of these guys I'm going to label as 15-degree increments. So pi over 3 should get me to 60 degrees. So I should be right on the line, just to kind of the left of that 60-degree marker there. Okay, and on that line I should be out 2 units. So I find 60 degrees. And I've already drawn that green arrow at the 2 radial marker, right? So 2, there's my point, 1, 2, 3, all the way to 8 here. Those will give me my radial distances, okay? So the radial distance from the origin at that point should be 2, and we see that about right there, okay? So that's the point 2 pi over 3. Whether you find the radial distance first or the angle first, I think it's usually easiest to go around your circle and actually find that theta coordinate, right? Figure out which angle you're at, and then go out however many radial units. Right? This is a little bit more difficult if you don't have this graph paper, right? Because we have exactly kind of a typical picture for graphing these points. Whereas on just a blank sheet of paper, which you probably have in front of you, like I said, you probably want to find that pi over 3, that 60 degrees, that's still in the first quadrant as it always has been, and then just go out 2 units. The distance from the origin should be 2. Let's do another point, this time 3 minus pi over 6. So of course I can still have negative theta values and negative r values, and I'll kind of show you how those work in just a minute. This negative pi over 6 here is kind of how I start thinking about this point. Negative theta is in the clockwise direction. So instead of going around counterclockwise, I'm going to go down instead from the polar axis. And what I find there is my radial distance of 3, and then pi over 6 is really like 30 degrees. So that's 2 tick marks on my graph. So you see my arrow there. This point then, I go negative 30 degrees, should be right at the end of that arrow, but just at the 3 radial distance mark, right? So that 3 there's my point. My radial distance is 3, and I have the point 3 minus pi over 6, okay? Now, we know based on our unit circle and our trig chart that we get all kinds of the same values kind of from different points on our circle, right? That doesn't really change here. In fact, I'm able to list these 2 points kind of a couple different ways, okay? So really what happens here, this point r theta can be written also as r plus theta plus 2 pi, right? If I go around my circle another time, I'll end right back up at the point I started it at. So to add 2 pi to any y coordinate, any theta coordinate, I'll end up back where I started. But also I can do a little bit more kind of different stuff. If I think about having a negative r value, and I'll show you how that works, we'll kind of go backwards through the origin instead of out from the origin. But if I do that, then I have to add not a whole circle around, but just a half, add a pi. So this 2 pi over 3, I can write as 2 comma pi over 3 plus 2 pi should be, 7 pi over 3? Right? And I can also think about this as being negative 2, and pi over 3 plus pi should be a 5 pi over 3. Okay? So all of those guys are just the different ways to represent really the same coordinate point. We don't really have that in the rectangular system, right? The point 2, 3 is the point 2, 3. I can't get to it any other way. Right? So this is just kind of one of the intricacies of this polar system is we have multiple ways to reach the same point. You don't necessarily have to go above and beyond to find the point that I'm talking about, right? You don't necessarily have to be too creative. If I ask you to plot the point, 2 pi over 3, you can just go about it the normal way. You don't have to go 2 and then around the circle twice, you know what I mean? So you have a little bit of freedom, but it's just an interesting thing. So we need to be able to convert from one system to the other, right? So I want to be able to go from rectangular coordinates back to polar, or polar back to rectangular. Whatever direction it is, I need to have a way to do that, okay? So because the points we have, x, y, are going to lie on a circle here, on the circle with radius r, what we're going to be able to do is extract what x and y are in terms of r and theta, right? There's a lot of trig involved in this, of course. So again, the reason our point lies on the circle is because on our polar system, everything kind of lies on a circle. We don't just really have anything floating out in random space. They're all going to be on a circle somewhere. So if that's the case, we're going to be able to use our Pythagorean theorem, our formula for a circle, if r is positive, and then our tangent of theta is also going to be y over x. Now let me show you where those come from. I'm going to copy down our picture from before here. So there's our radial point, our point r theta, with r and theta shown. Now what I've drawn here is a perpendicular down to the polar axis, right? That dotted line there. And I'm showing that makes a right triangle, okay? That means that the x and y coordinates of this point, the x and y coordinates, I can extract as the x and y distances from those radial, or from that perpendicular, right? So from the origin to that perpendicular is x in the x direction, and then going up is the y value, okay? So if I have r and theta, I need to be able to get x and y, vice versa. X I can find by using sine of theta. Oh, I'm sorry, I said it backwards. Y I can find by using sine of theta. Sine of theta is struggling today. Y over r. opposite over hypotenuse. Cosine of theta is, of course, adjacent x over hypotenuse. These four little equations will really be how we go back and forth from one point to another point for polar and rectangular. So when we're converting, let's do first from polar to rectangular coordinates. The equations that we'll use are the following. Given some r theta, I can find x by r cosine theta and y by r sine theta. That's it. Going from rectangular to polar is a little bit more difficult. We are given some xy and we want to find r and theta. To find r, we do r squared equals x squared plus y squared. We'll have to solve for r. And we also use tangent of theta is y over x, but we need to be careful. This tangent of theta is important. We need to be careful here because to solve for theta, we use inverse tangent, and inverse tangent has restrictions. Okay, and I'll outline those on the next page. I'll just go through them relatively quickly, but in practice, it's a little bit easier than what I make it seem like here. Okay, so tangent of theta is y over x. That means theta is equal to, we get a couple different things. This is a piecewise definition. It's equal to the inverse tangent of y over x as long as x is positive. And it's equal to tangent of y over x plus pi if x is negative. Okay? And the reason we're doing that there is because inverse tangent's domain is restricted, right? It's restricted from minus pi over 2 to pi over 2, okay? So what we have to do is think about this a little bit extra, but I'll show you that it's not so bad in practice. We also have points that lie on the vertical axis, right? Like I can graph the point 0, 3 on the y-axis. So I should be able to do that with polar coordinates. However, that's going to give our inverse tangent an undefined value, right? So what would happen is x would be 0 in that case. And if that happens, and we're on the vertical, the positive y-axis, y's got to be positive, and we're at the angle of pi over 2, okay? We can be on the negative y-axis or an angle of minus pi over 2 if x is 0 and y is negative, okay? So try to keep this in mind. You can go back or you can and look back in your notes at this here when we're working through these conversions next. But I will use this kind of formula to figure out what theta is when converting from rectangular to polar. First, let's convert these rectangular coordinates to polar coordinates. So hopefully this will be the harder conversion to do, and I'll iron it out so that it makes as much sense as I can. Let's do that first point first, 1, 1. So if I have xy, I can find r by r squared equals x squared plus y squared, and my x's and y's are both 1 here. So really all I have is r squared equals 2. So r should be plus or minus 2. Plus or minus. Which one is it? Well, think about the point you have. This point, where is it? What quadrant? 1, 1's in the first quadrant. So that means a radial distance of positive square root of 2 makes, I think, the most sense. Going out positively in the first quadrant, we can pretty much always have a positive radial distance. Okay, so I don't really necessarily have to worry about the minus here. We know from one of the previous slides that we can write these polar points with a negative r, but I don't really need it here. Okay, this is the point 1, 1, and it's in the first quadrant, so r equals square root of 2 should work just fine. Okay, x is positive, so theta should be tangent inverse of 1, right? Of y over x, 1 over 1 is 1. I need inverse tangent of 1. What angle makes my tangent of theta equal to 1? Well, that has to be pi over 4. Okay? This is the nice situation to be in. So the point 1, 1 really gives square root of 2 pi over 4. That inverse tangent, there was nothing weird about it. The angle that gives tangent is pi over 4. Oh, I'm sorry, that gives tangent as 1 is pi over 4, right? We don't have to go negatives, backwards, upside downs, because that's in the first quadrant. Pretty much everything is as we want it, okay? The next point, negative 1 square root of 3. I find my r value the same way. R squared is minus 1 squared plus square root of 3 squared is 4. So r is plus or minus 2. And I really don't need the plus or minus. All right, I can pretty much just use that positive 2, and I'll show you that. X is bigger than 0. So theta, x is less than 0. Forgive me. X is less than 0, right? I'm in the second or third quadrant here. In fact, I'm in the second quadrant because I'm to the left one and then I'm up square root of 3 units, right? So what I'm finding the inverse tangent of is negative square root of 3. X is less than 0. So what that means is I have to take the inverse tangent of square root of 3. Inverse tangent of square root of 3 happens to be minus pi over 3. Inverse tangent of minus square root of 3 happens to be minus pi over 3. Okay, tangent of minus pi over 3 is minus the square root of 3. And what I have to do to that is add pi. Because my angle here, like I just said, I was in the second quadrant. Minus pi over 3 is in the fourth quadrant. Okay, so I could either do angle that puts me in the fourth quadrant and then a negative r, or I could do an angle that puts me in the quadrant I'm supposed to be in and that positive r that corresponds. Okay, so adding that adding that pi puts me at 2 pi over 3. And that makes sense because that is in the third quadrant. My point then should be 2 comma 2 pi over 3, and that's in quadrant 2, which makes sense. Negative 1 square root of 3 should be in that second quadrant. Those are the difficult conversions, right? Because there are options, right? There are different options for finding r. There are different kind of options for finding theta. Okay, like I said, if you want, this could also be written as the point minus 2 minus pi over 3. That would be the same, but it's just weird that way. It doesn't kind of make as much intuitive sense, I don't think. Next, we convert the points radical 3 pi over 6 and 3 pi over 2 to rectangular. These are easy because what we're able to use here is just x equals r cosine theta and y equals r sine theta. That's all we need. Okay, so this point first, x equals r cosine theta. There it is. R is radical 3. Cosine theta is pi over 6. I just have to remember some of my nicer trig values. R is radical 3. Cosine of pi over 6 happens to be radical 3 over 2. So this point does indeed simplify down to 3 halves. So the x-coordinate is 3 halves. The y-coordinate should be r sine theta. And that boils down quickly. Sine of pi over 6 is 1/2. So my point is 3 pi over 2, comma, 3 over 2 and radical 3 over 2. That's it. Those are easy. Same thing here. X equals r is 2. Cosine of theta is 3 pi over 2. So I go through and I find, so in this case, cosine of 3 pi over 2, that's down kind of 270 degrees, and cosine of that angle is 0. Okay, that's an okay thing. It's interesting, but it's okay. Y to sine of the 3 pi over 2 should give me 2 times a negative 1, which is minus 2. So this is the point 0 minus 2. Where's that at? That's on the negative y-axis. 0 minus 2. The corresponding polar point is still 3 pi over 2. But that kind of makes some sense, right? 3 pi over 2 is all the way around almost my radial axis there till I'm on that negative y direction, right? There's my angle. So then there's my conversion from polar to rectangular. Okay. Another cool thing that we have here, if I can show you, if I just graph r equals 3, if I go out 3 radial units, r equals 3 is just a circle with radius 3. So that's the equation that I have, right? Like r of theta equals 3 corresponds to that circle, where we write it as x squared plus y squared equals 9, right? It's an interesting thing. That is a circle with radius 3 written in polar coordinates. Okay. We also, of course, want to be able to find slope here. I know this video is getting a little long. Bear with me for a little longer. We want to find slope of a polar graph. Okay. So if I have r as defined as a function of theta, right? So kind of similar to what I just did on the previous slide with that circle, I want to find the slope. And basically we're going to do this kind of the same way we did in parametric equations. Parametrically, we wrote kind of x of t, but now let's use x of theta. And here I'm going to do something a little unique, right? Remember, x equals r cosine of theta. I'm just going to do a little bit notationally. If r is f of theta, then I'm going to write r there as f of theta, right? So that guy and that guy are the same. So r cosine theta, or f of theta cosine theta, and y is f of theta sine of theta. Okay, so my parametric equation here, I'm going to find both of these derivatives with respect to theta. Okay, so I got some product rule going on here. I have a function of theta times cosine of theta. So that derivative, x prime of theta, is derivative of first times the second minus the second times derivative of the first. Right? And what I see there is f prime of theta, cosine of theta. Derivative of cosine was a minus sign, and that's why that negative's there. Derivative of y with respect to theta is f prime of theta, sine of theta, plus f of theta, derivative of sine is cosine of theta. And we remember that our parametric derivative is dy over dx, is dy d theta in this case over dx d theta. So as far as our parametrics go, usually we do t. I'm just saying, hey, think about t as being theta here, because the theta we have in our polar coordinates, I want to see in this polar derivative. But I want to think about the derivative as kind of y over x, change in y over change in x. So that's why we see dy dx there. So now when I plug in, right, dy d theta, there is the same as y prime. That's the same as y prime. So I'm just going to write that down again. And I did them upside down. Dang it, let me fix that. Okay, I fixed it. I'm sorry about that. So what happens here, we have y prime on top in green. I had them reversed for some reason. Happens. And our x prime down below, dx d theta, is there as x prime. And there is our derivative of a polar equation, kind of in thinking about it in an xy sense, right? Change of y over change in x. Okay, so what this looks like is really pretty straightforward. But one of the main things that we'll look for are horizontal and vertical tangents, kind of as before, right? Horizontal tangents we get if the derivative of y with respect to theta is 0. And that makes some sense because the equation dy dx equals 0 is 0 when the numerator dy d theta is 0, right? So that occurs when the numerator here, dy d theta, is 0. And then vertical tangents arrive when the slope is undefined. And that will correspond to having vertical tangent, slope is undefined, if dx d theta there is also 0. Okay? So we won't really do the two simultaneously for the most part, right? We'll be checking to see if the derivative is 0 or if it's undefined, right? But since this derivative is defined as a quotient, we're able to kind of take it apart and look at the numerator and denominator separately. Okay? So let's work through this. Let's find a slope here. Find the horizontal and vertical tangents of r of theta is sine of theta from 0 to pi. So there's the domain of my function. R of theta is sine of theta. So basically, how we do this, I can't just look at like r prime, right? Unfortunately, it's not quite that straightforward. That would be the rate of change of r with respect to theta, right? And that's fine. That's fine. But it's in a different context than we're used to, right? We want to think about this as the change in y over change in x. So for us, we look at dy dx or dy d theta divided by dx d theta. So if r is sine of theta and x is r cosine theta, then x should be sine theta cosine theta. So I'm plugging that theta in, or I'm sorry, that r in for x, right? X equals the same r there, sine of theta is replaced. Okay, so I just have sine theta cosine theta. And y is equal to r sine theta. If r is sine, then y is just sine squared of theta. Okay, so I'm going to look for horizontal and vertical tangents. Again, horizontal tangents, we see when dy d theta is 0. And I'm just going to go right ahead and take that derivative. So I have y as a function of theta, right? Y equals sine squared of theta. So its derivative should be, I bring the 2 down, sine of theta stays the same, derivative of sine is cosine. Okay? There's my dy d theta. I need to set that equal to 0 and solve. Okay? So I need to figure out when sine and cosine are both give me 0 at once. Well, if you notice, it's a little bit easier. This is a double angle formula. Sine of 2 theta equals 0. This is a little just bit easier to handle. So when is sine of 2 theta equal to 0? Well, sine of theta is 0. This is true when 2 theta is equal to 0, pi, and 2 pi. Now, of course, 2 pi is outside of my domain. But remember, I'm working with 2 theta here just for a second. And I'm going to divide that all by 2 to get theta equals 0, pi over 2, and pi. Well, pi is still outside of my domain because my thetas are going from 0 to pi, not including pi. So I can get rid of pi. And then the 2 theta values that correspond should be 0 and pi over 2. Those are the angles where I have horizontal tangents. Okay? What are those points? What are the points at which I have horizontal and vertical tangents? Well, when theta is 0, r is also 0 because r is sine of theta. So I have points 0, 0, right? When theta is 0, r is also 0. And when theta is pi over 2, r is 1. Those 2 points are the locations of horizontal tangent lines. I want to do the same thing here, but now I'll try to find vertical tangents. For that, we need x equals r cosine theta, which we said was sine theta cosine theta. Vertical tangents are when I take a derivative of x here with respect to theta. And I have product rule, right? I have sine times cosine. So the product rule, dx d theta, gives me sine of theta times minus sine of theta plus cosine of theta times cosine of theta, or in other words, minus sine squared theta plus cosine squared theta. Okay, this happens to be another double angle identity, right? And it just makes things a little bit easier to solve when I set them equal to 0. That's the same as cosine of 2 theta, and I want to know when that guy is 0. And that occurs when I take inverse cosine of both sides. Inverse cosine of 0 happens to be What are we looking at? 2 theta equals pi over 2 and 3 pi over 2. I'm also going to include 5 pi over 2 because I'm going to divide all of these by 2. I have to think about all the things that end up in the domain from 0 to pi. Right? So when I divide everything by 2 here, I have pi over 4, 3 pi over 4, and 5 pi over 4. And 5 pi over 4 just happens to be still outside of my domain. So the two theta values that I get where my tangents are vertical, slope is undefined at these points, are when theta is pi over 4 and 3 pi over 4. When theta is pi over 4, sine is radical 2 over 2. And when theta is 3 pi over 4, I actually have the same value there for r. Okay. Those are the two polar coordinates, the polar points where tangents are vertical. Okay, I hope you enjoyed this. I want to post one more example of these derivatives here. Thank you for watching.